Welcome to Cognitive Spirals, exploring the latest research into consciousness, cognition, and machine intelligence.
Excited to be diving in today. The topic of compute optimal scaling, specifically knowledge versus reasoning, is something I've been wrestling with for a while now.
Absolutely. It feels like we're hitting a wall with just throwing more data and parameters at the problem. We need to be smarter about how we're allocating computational resources.
Exactly. It's like we're trying to build a bridge by just piling up more rocks instead of actually understanding the principles of structural engineering. We need a new approach to the underlying algorithms.
I think that's a great analogy. It seems like the current paradigm is very focused on scaling up existing deep learning models, but maybe we're missing something fundamental about how intelligence actually works. I mean, at what point does simply increasing the size of the model stop yielding proportional returns in terms of actual reasoning ability?
Well, that's the million-dollar question, isn't it? We've seen impressive results with massive language models, but they still struggle with tasks that require common sense or abstract reasoning. It's almost like they're incredibly good at memorizing patterns, but they don't really understand what they're saying.
Right. They can generate grammatically correct and even seemingly insightful text, but they lack the ability to connect it to real-world knowledge or to reason about cause and effect. It's all surface level.
And that's where the spatiotemporal aspect comes in, I think. They don't have a good internal model of how things change over time and space. They're trained on static data sets, but the real world is dynamic. How can they reason about something they can't properly represent?
I see what you mean. Think about how humans learn. We don't just passively absorb information. We actively interact with our environment and build up a mental model of how things work. And that model is constantly being updated as we encounter new experiences.
But isn't that exactly what deep learning is doing, just at a different scale? We're feeding these models vast amounts of data, and they're learning to extract patterns and make predictions. Isn't that a form of model building, even if it's not explicit?
I would argue that it's a very different kind of model. Deep learning models are essentially black boxes. We don't really know what's going on inside, and it's difficult to interpret their decisions. With symbolic systems, on the other hand, we have explicit representations of knowledge and clear rules for reasoning. We can actually see how the system is arriving at its conclusions.
And that interpretability is crucial for building trust, especially in high-stakes applications. Imagine using a self-driving car that makes decisions based on some inscrutable deep learning algorithm. How can you be sure it's going to behave safely in all situations?
Yeah, that's a really important point. I mean, we need to be able to understand why an AI system is making a particular decision, not just that it's making the right decision most of the time. It's about accountability.
Okay, but isn't it possible that we'll eventually be able to open up these black boxes and understand how they work? Researchers are already making progress in interpreting deep learning models using techniques like attention mechanisms and saliency maps.
That's true, but even if we can get a better understanding of what's going on inside the model, it still doesn't address the fundamental problem of knowledge representation. Deep learning models are good at recognizing patterns, but they're not good at representing abstract concepts or reasoning about relationships between them.
And that's where the coordinate representation idea comes back in. How can you represent abstract concepts in a way that allows you to reason about them spatially and temporally? How can you translate between different levels of abstraction?
That's a great way to frame it. I've been thinking a lot about the brain's ability to integrate different modalities of information. We can seamlessly combine visual, auditory, and tactile information to make sense of the world. How can we design AI systems that can do the same?
Well, we're already seeing some progress in that area with multimodal models that can process both images and text. But it's still early days.
But are they truly integrating the information, or are they just treating them as separate inputs? It feels like they're still missing that deeper understanding of how the different modalities relate to each other.
Exactly. It's like they're seeing the individual pixels and hearing the individual words, but they're not grasping the underlying meaning or the relationships between them.
It's like trying to understand a joke by just analyzing the individual words without understanding the context or the cultural references. You might get the grammar right, but you'll miss the humor.
Okay, I see your point. So, if we're not just going to keep scaling up deep learning models, what's the alternative? What's the next frontier?
I think we need to explore neuro-symbolic approaches that combine the strengths of deep learning with the strengths of symbolic reasoning. We can use deep learning to extract features from raw data, and then use symbolic systems to reason about those features and make decisions.
And we need to think about how to represent space and time in a more explicit way. Maybe we can develop algorithms that are inherently capable of translating between different coordinate systems.
I think that a bio-inspired approach could be really fruitful. We can look to the brain for inspiration and try to understand how it represents and manipulates knowledge. How do neurons encode information? How do different brain regions communicate with each other? Can we translate those principles into AI algorithms?
That's interesting. I've always been a bit skeptical of bio-inspired approaches, but maybe there's something to it. I mean, the brain is a pretty amazing piece of engineering.
It's the only truly intelligent system we know of. It makes sense to study it and try to understand its principles. We don't have to copy it exactly, but we can certainly learn from it.
And maybe we can even discover new algorithms that are fundamentally different from anything we've come up with so far. Maybe the brain is using a different kind of computation that we haven't even considered.
That's a really exciting possibility. It could be a paradigm shift in AI research.
But wouldn't that require a completely new kind of hardware? Our current computers are based on fundamentally different principles than the brain.
Maybe, maybe not. There are already researchers working on neuromorphic computing, which is designed to mimic the structure and function of the brain. And even if we don't have specialized hardware, we can still try to implement brain-inspired algorithms on existing hardware.
The key is to understand the underlying principles, not just to copy the hardware. We need to figure out how the brain represents and manipulates knowledge, and then translate those principles into algorithms that can run on any kind of computer.
Yes. And going back to the idea of optimal scaling, it seems like we need to find a way to balance knowledge acquisition and reasoning ability. We can't just keep feeding the models more and more data. We need to make sure they're actually learning to reason with that data.
So, how do we measure that? How do we quantify reasoning ability?
That's a tough question. There's no single metric that captures all aspects of reasoning. But we can use a variety of tasks to assess different reasoning skills, such as logical deduction, common sense reasoning, and analogical reasoning.
And we need to design tasks that are challenging enough to really push the limits of the AI systems. We can't just rely on simple benchmark datasets that they've already memorized.
And maybe we need to move beyond traditional benchmarks and start designing tasks that are more ecologically valid. Tasks that reflect the kinds of reasoning challenges we face in the real world.
Like what? Can you give me an example?
Well, imagine a robot that has to navigate a cluttered room and pick up a specific object. It has to reason about the spatial relationships between objects, plan a path, and avoid obstacles. That's a much more complex reasoning task than just classifying images.
Or imagine a system that has to understand a complex legal document and extract the relevant information to answer specific questions. It has to reason about the meaning of the words, the relationships between the clauses, and the context of the document.
These are the types of problems that require a combination of knowledge and reasoning. And that's where the neuro-symbolic approaches in spatiotemporal reasoning come in, I think. Combining the pattern recognition of deep learning with the reasoning abilities of symbolic systems, and explicitly modeling space and time.
Okay, I'm starting to see the bigger picture. So, it's not just about scaling up deep learning models. It's about developing new algorithms and architectures that are better suited for reasoning and that can integrate different modalities of information. It's about combining the best of both worlds, deep learning and symbolic reasoning.
Exactly. And it's about taking inspiration from the brain and trying to understand how it solves these kinds of problems.
And it's about developing new ways to represent space and time in AI systems, so they can reason about the world in a more meaningful way.
Yes, and ultimately, it's about building AI systems that are not just intelligent, but also understandable, trustworthy, and accountable.
So, let's get concrete. What are some specific research directions that we should be pursuing in the near future?
From a neuroscience perspective, I think we need to invest more in understanding how the brain integrates different modalities of information. How do different brain regions communicate with each other? How do neurons encode information? We can use techniques like fMRI, EEG, and single-cell recording to study these questions.
And from a deep learning perspective, I think we need to explore new architectures that are better suited for reasoning. Maybe we can develop models that have separate modules for pattern recognition and reasoning, and that can communicate with each other in a more efficient way.
From a neuro-symbolic perspective, I think we need to develop new ways to combine deep learning with symbolic reasoning. Maybe we can use deep learning to extract features from raw data, and then use symbolic systems to reason about those features and make decisions. Or maybe we can develop hybrid systems that can learn both symbolic and subsymbolic representations.
And from a spatiotemporal perspective, I think we need to develop new algorithms that are inherently capable of translating between different coordinate systems. Maybe we can develop models that explicitly represent space and time, and that can reason about the relationships between events in different locations and timescales.
Yeah, I'm particularly interested in exploring how neurobiological principles of synaptic plasticity and long-term memory consolidation could inform the design of robust and adaptable AI architectures. How can we create AI systems that can learn from experience and adapt to changing environments, just like the brain does?
I'm intrigued by the potential of deep learning to drive a new frontier in AI and to further our understanding of cognitive processes. Is there any research exploring the development of deep learning architectures that are better optimized for efficient reasoning, rather than simply for pattern recognition? We need to move beyond brute force optimization and find more elegant solutions.
I agree completely. The reliance on massive datasets and deep learning seems like a form of brute force approach to intelligence, rather than a genuine understanding of the underlying principles of knowledge and reasoning. I'm curious if symbolic representations, combined with reasoning algorithms, could potentially achieve a more nuanced and efficient form of intelligence.
And I'm obsessed with this idea of a core algorithm capable of translating between different coordinate representations. It's so compelling, yet frustratingly elusive. I feel that we may be missing something fundamental about how the brain itself manages this kind of integration, possibly hinting at a different kind of algorithm that's currently beyond our reach.
Maybe a more practical next step would be to look at how current LLMs handle different coordinate systems internally. I mean, do they even have a standard or universal method for translating between them? That seems critical for effective multi-agent interaction and something we could investigate with existing models.
That's a great point. Analyzing the ratio of knowledge-based facts to reasoning capabilities in current large language models, LLMs, reveals a potential bottleneck in their development toward AGI. More data is crucial, but the algorithms themselves may not be optimally leveraging the knowledge they're absorbing, leading to inefficient scaling. So, let's study how they actually use that knowledge.
Yes, but we need to be careful not to get too caught up in the hype around LLMs. The current trend of using deep learning to solve tasks reminds me of early attempts at using supercomputers for tasks like weather forecasting. Yes, they might have produced results, but did they offer genuine understanding of the underlying physical principles? Deep learning often lacks that essential component of a sophisticated intelligence.
Exactly. The sheer scale of parameters in current deep learning models reminds me of a giant, poorly organized library. If the core algorithm is fundamentally broken because it can't efficiently navigate this library of knowledge and translate between different forms of representation, what are the real limits of data-driven approaches to AGI? Are we building magnificent castles on shifting sands?
It's fascinating to ponder the potential of using a neuroscience-informed approach to create an embodied intelligence. If the goal is truly to model intelligent behavior, wouldn't integrating a sense of self and place in each agent, grounded in neurophysical principles, be a necessary prerequisite for success? And how would that impact the scaling of knowledge and reasoning?
That idea dovetails nicely with the challenge of multi-agent systems. Perhaps the current limitations of multi-agent systems are symptomatic of a larger problem within the field of deep learning, a problem that can be solved by understanding how different representations of spatiotemporal data can be effectively interconnected and used for complex reasoning.
The observed limitations of multi-agent LM systems in achieving complex, nuanced reasoning underscore the need for neuro-symbolic methods to provide explicit models of knowledge and reasoning. Deep learning on its own might be a tool, but is not the complete solution. And until we address this fundamental flaw, we will continue to see these systems stumble.
I agree. And it's frustrating to see progress stalled on multi-agent systems, especially when the problem seems directly related to a lack of explicit spatiotemporal reasoning. A more principled approach is needed, and I suspect this is where the key to AGI will lie. It all comes back to that core algorithm.
Well, it sounds like we're all on the same page, at least in terms of the challenges we're facing. It's going to take a multidisciplinary approach to solve these problems, and I'm excited to see what the future holds.
Me too. It's a really exciting time to be working in AI. There's so much potential and so much left to discover.
I agree. It's going to be a long and challenging journey, but I'm optimistic that we can make real progress in understanding intelligence and building truly intelligent machines.
Absolutely. And I think the focus on spatiotemporal reasoning and neuro-symbolic approaches is going to be crucial for unlocking the next level of AI.
Well, thanks everyone for joining me for this episode of Cognitive Spirals. It's been a fascinating discussion. And to our listeners, thanks for tuning in. We'll be back next week with another exciting topic.